Hey, what's up? It's Mr. Klinkerman again. We are finally moving on to Chapter 2. And what we're going to do in Chapter 2 is we're going to be looking at a specific type of function called a quadratic function. Now, you know in Chapter 1 we looked at functions, how you compose them, how you find their domain and range, how you find their inverses, how you translate them, reflect them, stretch them, so forth. Alright, now we're looking at quadratic functions in particular. And what we're going to begin with are two things in section 2.1. We're going to learn how to solve quadratic equations by factorizing. We normally say factoring, but IB uses the term factorizing a lot. And we're also going to look at how you solve quadratic equations by completing the square. And then in section 2.2, we'll do something else that you're pretty familiar with. We're going to solve quadratic equations using what's called the quadratic formula. These are all three methods that you need to be proficient at. And so we'll focus on them, make sure that you have all the necessary information in order to develop those skills. What I want to begin this lesson about factorizing with, though, is simply explaining what quadratic functions are, because you need to have an understanding of what you're working with before you go about trying to solve equations related to that thing. Alright, so what are quadratic functions? Well, quite simply, or maybe not so simply, I don't know. A quadratic function is any equation, any function that can be written in the form f of x equals ax squared plus bx plus c. And then I made the little note below showing that a, b, and c have to be elements of the real number. So these coefficients that you see, right there, and right there, the a, b, and c, they have to be real numbers, nothing more, nothing less. And so a couple of examples, three of them actually, of a quadratic function. Well, here you see an equation where it's written in the form ax squared plus bx plus c. Okay, where a is a coefficient for your quadratic term, and that would be -5. B is a coefficient for the linear term, it's just -5/3. And c is the constant term at the end, which is 21/4. Okay, so that's the form we're looking for. Now, not every quadratic function's equation is automatically written in that form ax squared plus bx plus c, but they all can be written in that form. I emphasize the word can. And here are a couple that are not written in that form to begin with, but that you can easily rewrite in that form just through following order of operations. Okay, this second equation here is in what you would call factored form. Alright, where we call the ax squared plus bx plus c standard form, or general form sometimes. And then this third equation is also not written in standard form, it's written in turning point form. Okay, I realize I need another n in turning. Alright, turning point form. But even though those factored forms and turning point forms don't look like the standard form, if you follow order of operations, if you carry out the multiplication here, if you square and then follow order of operations there, you come up with these two equations that are in the form ax squared plus bx plus c. And so any function such as those that can be written in the form ax squared plus bx plus c is a quadratic function. And one of the things that you guys ought to know about quadratic functions already is that the graph of a quadratic function is called a parabola. And parabolas are one of the most useful graphs that you see in terms of their real-world applications. Alright, we'll talk through a couple of those. One of those, you can frequently see the use of parabola in architecture, as you see here with the base of the Eiffel Tower. Arches are often in the shape of parabolas. And another common use of parabolas or application is with what's called projectile motion. Anytime something is thrown or jumps or is dropped, you can use a parabola to model its motion. And I don't know how well you can see this little guy right here, but this is a picture of a ramp with a stunt biker making a jump over a river basically from this ramp, and the path that his jump follows is a parabola. Okay, there are many other applications, but those are some common ones that you're going to see. Now, enough with all the background information. we need to learn, well, not quite enough with all the background information. I actually got a little bit more for you, but then we're going to learn how to solve by factoring. The last thing I want to talk about in terms of background information is this. When you're trying to solve a quadratic function, you need to understand how the solution that you find relates to the graph. And I've given you an equation of a quadratic function. It's written in factor form, but it's still a quadratic functions equation. And then I showed you the graph along with it. And I want you to read this. All right. The solutions of a quadratic equation correspond with the x-intercepts, or the roots of its related graph. Every time you're trying to solve a quadratic equation, you're trying to find the value of x that makes y equal to 0. You're trying to find, another way of saying it is, where would the related graph of that equation cross the x-axis? And we already talked about the three different methods you can use to figure that out, but in this graph, for instance, -1 is one of the values of x that makes y equal to 0, and +3 is another value of x that makes y equal to 0. We're trying to find the values of x that make y equal 0, or find the x-intercepts of a quadratic function whenever we're trying to solve its related equation. Now let's get into solving the equations. Now, we spent a lot of time factorizing quadratic expressions when we were covering the prior knowledge section of the course. And so a lot of what we're going to do, you have a good idea of how to accomplish already. If we're going to solve by factorization, one thing you've got to keep in mind is that we're going to set the equation equal to 0. Now you notice this equation doesn't have an f of x in it, but it has a quadratic expression. On the other side there's a 0. In other words, we're letting y, or f of x, be 0, because we're finding the x-intercepts of the graph. Alright, and then once you've done that, you simply want to find the factors of that related quadratic expression. X squared plus 11x plus 24. We're finding factors of 24 that add up to 11, and you know that those are 8 and 3. And so we can factor that into x plus 8 times x plus 3. Now, what are the solutions? Okay, well, we're going to make use of something called the zero product property. And I'm going to put that on screen in a moment. If I put it up now, it's going to erase what I've already written. But here's basically the idea. We have a product of two numbers, and we're saying that product is equal to 0. And in order for that to be true, we would have to say that either the first factor is equal to 0, or the second factor is equal to 0. In other words, either x plus 8 equals 0 or x plus 3 equals 0 if the product of those two values is equal to 0. And so I wrote equations where I set each factor equal to 0, and I'm simply going to solve those equations, and that gets me my solutions. X equals -8, x equals -3. Alright, and you could plug each of those in and check your answer, but you will find that when you substitute -8 in for both the x's, or -3 in for both the x's, it will give you 0 on both sides of the equation. Alright, here's that zero product property written out now that I can afford to get that work off the screen. And again, just emphasizing that if you multiply two numbers and you get 0, then either the first of those factors is equal to 0 or the second factor is equal to 0. Now for us, we're going to be using this a lot. If you have the factor form of a quadratic equation, x minus a times x minus b, and that's equal to 0, then x minus a equals 0 or x minus b equals 0. One of the two factors has to equal to 0. Alright, let's solve another equation. And you have to use a variety of factoring methods. None are too difficult because you've done them all before. If we're going to solve this equation m squared minus 49 equals 0 by factorizing, well, I hope you recognize that this is a difference of two squares pattern. M squared is a perfect square, so is 49. And you factor differences of squares into conjugate pairs. In this case, that means this is going to become m plus 7 times m minus 7 equals 0. And then we'll use the zero product property again, that is in that box in the top right corner, and set each individual factor equal to 0. And you see here that we get two solutions, m equals -7 and m equals +7. And now another thing I should point out about quadratic equations, and you can determine this by the degree of the polynomial, is that they do have two solutions, although sometimes it's the same solution twice. You'll see examples of that at some point throughout this chapter. All right, one more simple factorizing question to go through. Now, I say simple, and you look at this and you might say it's not so simple, but it still is when the equation is not set equal to 0 to begin with. But in order to make use of the factorizing process and the zero product property, we have to set the equation equal to 0. And so what I'm going to do is I'm going to subtract 12n and 20 from both sides of this equation to begin. And that's going to give me n squared minus 2n minus 15 is equal to 0. And once that happens, now I can find the factors of negative 15 that add up to negative 2, and those are negative 5 and negative 3. Sorry, positive 3. Then set each factor equal to 0. And you've got your two solutions, n equals 5, n equals negative 3. Okay, now in each of those circumstances, the quadratic term had a coefficient of 1. You can say the value of a was equal to 1. I also want to show you when a is not equal to 1, what you do. When a is not equal to 1, you have to use that process factoring by grouping that we talked about. Now notice this equation is already set equal to 0, so that's good. We're finding the y or the x-intercept because y is equal to 0. And we want to multiply a times c here in order to factor by grouping. So we're going to say a times c equals negative 30. And then we're going to find the factors of negative 30 that add up to positive 1 because that's the coefficient of our linear term. And those factors are going to be positive 6 and negative 5. All right, and then remember you're going to rewrite that middle term, the linear term, as the sum of 6x and negative 5x, those two factors of a times c that added up to b. Then we're going to find the greatest common factor for the first pair of terms. All right, they have a greatest common factor of 3x, leaves us with x plus 2. Then we'll find the greatest common factor for the second pair of terms. And we're going to include the negative that's in front of the negative 5x. That's negative 5. And that will leave you with x plus 2 as well when you factor that out. And so the factored form here is 3x minus 5 times x plus 2 equals 0. All right, not nearly as difficult as you might have thought. Then we'll set 3x minus 5 equal to 0. Each factor gets set equal to 0. And you'll get x equals 5/3 and x equals negative 2 for your solutions. All right, let's try another. This one's a little simpler than the last one if you notice that it's a difference of squares pattern again. 25r squared and 4 are both perfect squares. We can just take the square root of each. And then write those square roots using conjugate pairs. We can say this is 5r minus 2 times 5r plus 2 is equal to 0. If you set 5r minus 2 equal to 0, you're going to get r equals positive 2/5. If you set 5r plus 2 equal to 0, you're going to get r is equal to negative 2/5. Alright, I have one that I want you to try on your own right now. It's going to be a little complicated, but you know all the fundamentals as far as how to do it. Okay? Now, this equation is not set equal to 0 right now for 1. What you're going to need to do is you're going to need to go ahead and take care of the distribution on each side of the equation. So multiply 5t times t plus 6, multiply 8 times 2t minus 1. And once you've done that, set the equation equal to 0 and solve by factoring. Try it out now. Okay, there you see the solution worked out on your screen. I did the distribution property like I talked about. Then I set the equation equal to 0. And then I factored by grouping by multiplying a times c, getting 40. Finding the factors of 40 to add up to 14, which were 10 and 4. And then following the same process that we did in part A on this example. If you have more questions about that, feel free to ask me in class. But we need to move on to a couple last examples. And these are applications, places where you can actually use quadratic equations in factoring. All right. It says here in this first example that the product of two positive integers, where one integer is 10 more than the other, is 96. And it wants us to find the integers. All right. Well, the place we're going to have to start right here is this. There are two numbers that we're trying to find. We know that one is 10 more than the other. And we know that the product of the two is 96. Okay, so the product equals 96. And let's say we call the first integer x. Well, since the second one is 10 more than the first one, we can say that second one is x plus 10. So if the product is 96, that means x times x plus 10 would be 96. Follow so far? Good. So we're going to get then x squared plus 10x equals 96. And then we're going to try to solve by factoring, so we want to set the equation equal to 0, and that'll give us x squared plus 10x minus 96 is equal to 0. Now, I don't know if you know your factors of negative 96 quite so well, but it turns out the factors of negative 96 that will add up to positive 10 are going to be positive 16 and negative 6. And so the solutions to the quadratic equation are x equals negative 16 and x equals 6. Although, if you look at the problem, we can't use both of those numbers. All right? Because we're looking for two positive integers, and one of the ones that we got was negative. So we're going to exclude the x equals negative 16 possibility. But let's say that we do use x equals 6, which we need to. That's our solution. We still need to find the two integers whose product was 96. Well, remember those integers were x, so 6, and then 10 more than x, so 16. So 6 and 16, that's your answer there. All right, got one more problem for us to try. Not easy, but you understand the basic concepts of it already. I've given you a right triangle, although I didn't draw the right angle on there, so let me take care of that right now. Given you a right triangle, and I've given you the side lengths to that right triangle in terms of x, and I'm asking you to find out what the value of x is. Well, whenever you have a right triangle, and you're trying to make a relationship between the side lengths, I hope that you think of the Pythagorean theorem for that. We are going to make advantage of the equation a squared plus b squared equals c squared. And of course, c always has to be the hypotenuse, and a and b can be either of the legs, so I'll label them that way. What we need to do then is make this equation. We're going to substitute x plus 7 in place of a. We'll substitute x in place of b. And we'll substitute x plus 8 for c. And what I'd like you to do is go through and solve that equation now. Try it. All right, now the thing I'm requiring you to remember here that we haven't talked about explicitly in this set of notes is how you square a binomial x plus 7. And if you have questions about how you square that binomial to get x squared plus 14x plus 49, and how you would square x plus 8 to get x squared plus 16x plus 64, you need to ask. But that's what I've done. And then in the next line, I combine the like terms. And now what I'm going to do is I'm going to go ahead and set the equation equal to 0. So I'm going to subtract x squared from both sides. I'm going to subtract 16x from both sides. And I'm going to subtract 64 from both sides. And then we'll factor. Turns out to be exactly the same expression that we were factoring earlier. except we had n's instead of x's. We already said the factors of negative 15 added to negative 2 are negative 5 and positive 3. And so you get x equals 5 and you get x equals negative 3. There were two solutions to the quadratic equation that we solved, although we are talking about a right triangle here. And with a right triangle, you cannot have negative side lengths, which means we need to choose x equals 5, and we need to exclude the negative solution that we got, because we can't have a side length of negative 3 for one of the sides of our triangle. That's solving quadratic equations by factoring with a few difficult applications, actually. Hope that makes sense. You have some problems to work with this skill. Try them out. Good luck.